Okay, thanks everyone for coming. This is the third lecture in the week on model-based derivative-free optimization. And so having kind of set some of the foundational ideas and some algorithmic ideas yesterday, today I want to look at extensions about how to make these methods more practical. So trying to kind of bridge that gap between things we can prove stuff about and things that work well in practice. So again, the context is the same as yesterday. We're looking at unconstrained, usually smooth, non-convex minimization. We're assuming Lipschitz continuous gradients mathematically, but no access to gradients in the software or in the algorithm. And we're using our trust region methods where we evaluate our function at some points near xk. We build a typically quadratic interpolation model that's going to locally approximate the objective, and then follow a trust region process. Calculate a step to decrease the model, evaluate the function at the new point, and make a decision whether that step was good or not. Okay, so today I want to talk about being a bit more conservative with function evaluations through a kind of geometry improvement process, and then kind of a bit of a laundry list of extensions of these ideas. So looking at constraints, noise, problem structure, and then a little bit of summary of some practical software choices and things at the end. So let's talk about geometry improvement. So as I said on Monday, one of the important use cases of DFO is expensive objective evaluations where finite differencing becomes kind of slow and impractical. But the method I spoke about yesterday, where we was essentially based around the idea that at every iteration with an xk and a delta k, we use that particular trust region to identify some nicely structured interpolation sets like coordinate perturbations that guarantee that our model has nice error bounds, for example, which leads to good theoretical results. What this means is that we can't really recycle any information across iterations, because at every iteration, we're either changing xk or delta k or both. So we basically, if we're using a set something like this, we have to throw away most, if not all, the information that we were working with previously. And in the case where objective evaluations are expensive in particular, that feels very wasteful. So what I want to talk about now is how can we retain interpolation points across iterations? How can we recycle information in a practical way to cut down the amount of evaluations that we use? The natural question that comes up once we do that is, how do we ensure our model is sufficiently accurate? How do we ensure it's fully linear? And if we're doing this process of adding and removing points, how do we decide which points we're going to keep and which points we're going to change? So if we want to retain some information across iterations, which information should we retain and which new information should we add? Which information should be removed? So for example, at every iteration, it probably makes sense to include the new function evaluation that we've just received, which is the function evaluated at our tentative trust region step. So let's have a look at how we might go about doing this. The main tool we're going to use to understand all of this are Lagrange polynomials. So this is a tool from approximation theory. They're a set of polynomials that are associated with a set of interpolation points. So this is a purely, there's no objective function in any case here. It's purely just the points that we're interpolating from. The way they are defined is, let's suppose we've got a collection of points in Rn, then we're going to have a family of polynomials. So there's going to be one polynomial associated with each one of our P interpolation points that again is going to map Rn to R. And the way we're going to define them is through this what quantity that I've got in red. So for the ith Lagrange polynomial, that is going to have a value of 1 when evaluated at yi, 0 when evaluated at any other of our interpolation points. So it's 1, so L1 takes a value of 1 at y1, 0 at y2, 0 at y3, and so on. And to kind of make this well defined, we assume that the degree of the polynomials are going to match the type of interpolation we're doing. So if we're doing linear interpolation, these polynomials are going to be linear and satisfy these interpolation conditions. If they're quadratic, if we're doing quadratic interpolation, Lagrange polynomials are quadratic, and so on. So this is the tool we're going to work with. This is not a DFO specific quantity. This is very kind of highly used, particularly in approximation theory. And to give you an idea of why this can be useful, this is a sort of traditional result from approximation theory. There's a textbook that you can look at for more details. So this is looking at interpolation in one dimension, but looking at high degree polynomial interpolation in 1D. So let's suppose we've got d plus 1 distinct points between -1 and 1, and we've got a univariate function going from that interval to R. What we're going to do if we've got d plus 1 points, distinct points, we'll be able to fit a polynomial of degree d to the function values at those yi points. And this result says that, well, we're going to have some error in our polynomial approximation. And with respect to the infinity norm, this error is within some constant of the optimal error of any degree d polynomial. So not one that interpolates at those points, but one that is just the optimal degree d interpolant in the sense of this norm. So our specific interpolant based on our specific interpolation points is within a constant factor of the optimal, where that constant factor depends on the choice of interpolation points. In particular, this quantity is called the Lebesgue constant. And the way you construct that is you take essentially the L1 norm of the Lagrange polynomials, and then you take a maximum of that L1 norm over your whole domain. So essentially thinking about the L1 norm of the Lagrange polynomials gives you that constant factor in how well this particular interpolating polynomial fits the function versus the optimal degree d interpolant. So hopefully this gives you some indication that these Lagrange polynomials do have some reasonable use in measuring the error of interpolation functions. So we're going to do something similar in our setting. So let's look at linear interpolation as the simple case. So P is n plus 1. First thing we need to do is construct the Lagrange polynomials. This is quite straightforward. If we're doing linear interpolation, the ith Lagrange polynomial is going to be a linear function where the constant and gradient terms come from forcing it to take the correct values at all the interpolation points y1 through yn plus 1. So it's going to be 1 at yi, 0 at all the other y's. And the way we can find C and G is we can solve this interpolation system. This is identical to the interpolation system defined yesterday, but instead of the function values f evaluated at each of our yi points, we now have a coordinate vector because we're forcing it to take a value of 1 or 0. So we can find the Ci and the Gi associated with Li by solving the same linear system as yesterday, but with EI as the right-hand side. What this means is if we go to evaluate Li at a particular point, well, we can write this as the coefficients Ci and Gi up to a scaling in a product with this vector that is essentially a basis for linear functions. So we've got a 1 and a y, essentially a scaled version of y. Now, we know C and delta G come from solving this linear system. In fact, this is essentially an M inverse EI with a transpose. So we've got EI transpose, M inverse transpose applied to this particular function. But what this means is that the ith Lagrange polynomial is EI in a product with something. So it's the ith component of a particular vector. As a result, a nice thing we can say is that if we want to evaluate all the Lagrange polynomials at a given point, we can solve this linear system here where M hat is our interpolation matrix. So one way of evaluating the Lagrange polynomials is to solve for all the Ci's and the Gi's, and then you can evaluate them at Y. But if you only need the Lagrange polynomial at a specific point, then you can get all of those values by solving one linear system rather than solving for each of the polynomials directly. So this is kind of a shortcut if you don't need the individual coefficients and you just need the vector of Lagrange polynomial values. So that's a nice little shortcut. And this is going to come in handy because some of you might remember yesterday when I was calculating the error bounds for linear interpolation, I was comparing my linear interpolation model to a linear Taylor series for my function evaluated at some point y in our trust region. And we got a bound that depended on the L1 norm of some vector v. There's the delta squared for our fully linear. But there was the L1 norm of a vector v, and v was designed to solve this linear system. That's how we constructed the v. If we go back, that is exactly the linear system that we're solving here for the Lagrange polynomials. So actually what I proved yesterday is this error bound. It says that the error between our linear interpolation model and a linear Taylor series is proportional to delta squared, where part of that constant is exactly the L1 norm of the Lagrange polynomials evaluated at the point where we're measuring the error. This is very similar to the Lebesgue constant, right? So the L1 norm of the Lagrange polynomials, the Lebesgue constant is a maximum over all y. Here we've got the L1 norm at a specific value of y, but we're measuring the error at a specific value of y as well. So this is kind of actually what we proved yesterday, written in a different form. Now, the L1 norm, the Lebesgue constant, is the more widely used constant in approximation theory. For our purposes, though, it's not going to be practical. So what I'm going to do is I'm going to switch to the infinity norm. So I'm going to say the L1 norm is bounded by p, because this vector is of length p, times the infinity norm instead. That's the quantity that we're going to be able to control more explicitly. So I'm going to substitute the L1 norm with p times the infinity norm in my bounds. Given this, I'm going to introduce this definition here. This is from a paper in 2007. And what I'm going to say is an interpolation set is going to be what I call lambda poised. So lambda is going to be some positive constant. It's going to be lambda poised for interpolation inside a particular region, inside a trust region. And what that is going to be defined as is similar to the Lebesgue constant. I'm going to take the infinity norm of my Lagrange polynomials over every point in my trust region, and I want that to be bounded by lambda. So if this were a 1 norm, we would basically get the Lebesgue constant. Now it's just the infinity norm, and I'm going to call it lambda poised, where lambda is this constant on the right-hand side here. So I'm basically taking a max over this error bound over all possible values of y. So now this constant lambda is going to be a numerical value that measures how good the interpolation set is in a geometric sense. So lambda only depends on the particular interpolation points. It doesn't depend on the function or anything like that. It's a purely geometric notion. And smaller values of lambda are better in terms of error bounds. However, there is a lower bound. In almost all situations, the base point of our trust region, essentially our current iterate, is going to be an interpolation point. In that case, we know that the Lagrange polynomial associated with xk takes a value of 1 at xk. Xk is a valid choice of y, which means that lambda must be at least 1 for this to be true. So we know that lambda is going to be at least 1. Larger values of lambda indicate worse geometry. So the result I mentioned just before for linear interpolation is equivalent to saying if you've got a lambda poised interpolation set, the corresponding linear interpolant is fully linear and the error bounds are proportional to your lambda poisedness constant, as well as some other stuff that's similar to what we had before. So there's like the delta squared in our function error bound, and you get the same thing in your gradient error bound as well. So this is just an alternative way of expressing our fully linear bounds that don't depend on these matrix norms that we had yesterday. And fully quadratic interpolation, you can construct the same thing. You can construct your Lagrange polynomials, you can maximize them, you can define lambda poisedness, you can get error bounds in terms of that quantity lambda. The other type of interpolation I mentioned yesterday is this in-between case between linear and fully quadratic with n squared over 2 points. This sort of minimum Frobenius norm interpolation. The way we need for this to work is we need to define our Lagrange polynomials, which are still going to be quadratic because it's a quadratic interpolating model, but we need to define them in kind of a minimum Frobenius norm type of way. So what I'm going to do, if I want to find Li, I'm going to solve a minimum Frobenius norm problem with the interpolation constraints that match what the values of Li are supposed to be at the points that I know. So this is sort of solving exactly the equivalent problem that we would expect. Once we do that, we've defined our Lagrange polynomials. We can define lambda poisedness in the usual way. So maximizing all the values of the Lagrange polynomial over all points in the trust region. And then I can get a similar result about fully linear error bounds. So a minimum Frobenius norm model is also fully linear. The constants are proportional to lambda, and the upper bound on the Hessian is also proportional to lambda. So this is basically the same as what I showed you yesterday, but I'm replacing matrix norms with the Lagrange, with the lambda poisedness value directly. So the reason that I've done this, the reason that we're looking at Lagrange polynomials as opposed to matrix norms, is that this becomes very useful as a way of deciding how to handle the interpolation set in the sense of adding and removing individual points. So how do we assess if an interpolation set is good? And if it is good, we're happy. If it's not good, how do we fix it to make it good? the Lagrange polynomials, the concept of lambda pointedness, give a very clear way of handling that. The way it works is like this. So let's suppose I'm starting with a particular interpolation set and I want to decide, is this set good enough? If not, how do I fix it? What points should I change to make it good? The first thing I need to do is calculate all my Lagrange polynomials and calculate the value of lambda. So maximize over all values of y in the trust region, maximize over all the Lagrange polynomials, the absolute value of Li evaluated at that point y. So compute the constant lambda, compute the lambda poisonous constant. Now, this can be a bit expensive. If we're doing linear interpolation, this isn't too bad to solve because all the LIs are linear. If we're doing quadratic interpolation, this does take a little bit longer, but you can do it by converting this into solving 2p trust region subproblems to global optimality. It can be a little bit slow, but nothing really significant. So let's suppose we calculate the exact value of lambda. The first thing I can say is I can just pick some arbitrary number, lambda star, and say, if lambda is smaller than this, I'm happy. So I'm going to pick some threshold value of lambda and say smaller than that, I'm happy with my interpolation set. The tricky thing then is to say, what happens if my lambda is too big? What happens if I have a bad interpolation set? It's actually very simple. What I have to do is, well, if my lambda is bigger than lambda star, all I have to do is find a y and an I where the associated Lagrange polynomial, the ith Lagrange polynomial, evaluated at this other point is strictly bigger than, sorry, this should be lambda star here. Find a value where this is bigger than lambda star, which we know exists because we've just evaluated the value of lambda, right? You can take the argmax of this, so which will give us a value of lambda, which is bigger than lambda star. And what we're going to do is we're going to replace the ith interpolation point, so whichever the Lagrange polynomial is, that yi, we're going to replace with the new point that gives it a large value. And that's it. We're going to make that swap. And then we repeat this process. This gives us a new interpolation set. We go back, calculate the new Lagrange polynomials, calculate the new lambda, and repeat the process. So every time we maximize, we swap out yi that comes from the I here with the value of y that from the argmax. That's all we're going to do. And there's a useful result that says this works, essentially. This terminates in finite time. Clearly, if it terminates, it produces a lambda star poise set. That's the definition of the termination condition. So the main part of the theorem is proving that it does in fact terminate in finite time for any value of lambda star strictly bigger than 1 and for any starting interpolation set. And that is a theorem that you can prove. I'm not going to go through the details, but the basic idea behind this, and this works for linear and quadratic and in fact higher order polynomial interpolation. But what you can show is for linear interpolation at least, and for quadratic, it's basically the same idea. If we make one of these swaps, or in fact, if we swap any point in the interpolation set with something else, we can look at what happens to the determinant of the matrix we use to solve the interpolation system. And what you can show is the determinant grows by a factor of at least the absolute value of the Lagrange polynomial associated with that swap. So if we delete yi and add in y, the determinant grows by at least a factor of the absolute value of that Lagrange polynomial value. In our geometry improvement algorithm, we've guaranteed that that quantity is at least lambda star. So what that means is every time we run this algorithm, the determinant of our interpolation matrix grows by a factor of at least lambda star. However, we've also set this up so that all our points are going to remain inside the trust region. So there is, because determinants are continuous, there is a global upper bound to how large the determinant can possibly get while all the points remain inside the ball. So we can't continue increasing it by a constant factor infinitely often. There's going to be some finite limit as to how much we can do it. That depends on the size of the determinant when we start. And you can prove this using Cramer's rule. I should note from my experience, this is the only time I've ever seen Cramer's rule actually be used for something. You might have had examples, but it's nice to actually see that coming up in a practical result. For minimum Frobenius norm, it's a slightly more complicated proof. It's not quite Cramer's rule, but similar results do hold. So this is what geometry improvement looks like. This is Very basic 2D example. So I'm looking to do linear interpolation in 2D. So here's my trust region centered at, in this case, the origin x1. And I'm doing 3 points because I'm doing linear interpolation in 2D. So let's suppose I start with the origin and these two other points, x2 and x3. And I've deliberately chosen x2 and x3 to be close together, which is how you can get lambda to be fairly big. In this case, lambda is about 14. This is still actually small, but I needed them sufficiently far away that you could actually see it on the diagram. So let's imagine that these are much closer together. You can get lambda much bigger. If I go and compute the Lagrange polynomials and maximize them in the ball for all of these, the largest value, this lambda of 14, comes from the Lagrange polynomial associated with x3. So that's going to take a value of 1 at x3 and 0 at x2 and x1. So you can imagine it goes from 0 to 1 as it moves from x2 to x3. So in the vertical direction, L3 is increasing very rapidly or changing very rapidly, large gradient. And so it can take a large value. It takes 14 somewhere either up the top or down the bottom. So if I make a swap, I believe the maximum, the argmax is at the top. So we're going to replace x3 with a point up the top. And if I do that, my new value of lambda has dropped from 14 to 2. And now I've just got the coordinate axes. I can, however, continue this process. The argmax, so this lambda equals 2, comes from the Lagrange polynomial associated with x1. So that takes a value of 1 here and 2 at each of the coordinate axes. So it's changing kind of along the 45-degree line. And the maximum value happens over in this bottom left corner. That's where lambda equals 2 happens. So what I'm going to do is replace the origin with the point over here. And if I do that, lambda drops down to 1.06. And as I say, lambda, because the points stay inside the trust region, lambda is bounded below by 1. So in 2 iterations, we've dropped from by 1 order of magnitude. So it's a fairly efficient process in practice. So that's how we can incrementally improve our geometry one step at a time. Now, if we go back to how we're building our model, for our interpolation set to be good, what our theory says is we want all of our points to be close to our current iterate. So we had something that said it has to be within order of magnitude delta distance away from our current iterate. Now we also know that we want our points to be lambda poised, so our Lagrange polynomials can't be too big. So this is what we want for fully linear models. So what we want to do is make sure our algorithm guarantees that this occurs at least sufficiently often. And what we're going to do is use this idea of how can we improve the lambda poisedness incrementally to get what I'm going to call incremental geometry improvement algorithm. It's from 2010. This does have theory and is also the basis of practical algorithms. But before we go to all that effort, I do want to just mention that I am spending a lot of time focusing on the geometry of the points, this lambda poisedness idea. What would happen if I only worried about the distance to xk? Maybe it would just happen that the points naturally don't get too bad in terms of their lambda poisedness. Maybe that's just going to come automatically. So what happens if I run an algorithm where all I care about is moving far away points close to my current iterate? What's going to happen? Well, it turns out it doesn't work. This paper has a nice counterexample where if you run a simple trust region method and all you do when you decide which points are going to be added and removed from the interpolation set, if you only ever consider distance to the current iterate, what's going to happen is all your interpolation points end up going along a subspace. And so you end up with a set where the linear interpolation or the interpolation system is singular. So this doesn't work. You have to explicitly take into account geometry when you run these methods. So you have to explicitly take into account lambda poisedness. So how do we do that? This is what the algorithm looks like. It's very similar to what we did yesterday. So I'm going to say, given our current choice of interpolation set, build our model, minimize the model to calculate a step, evaluate the new point, decide whether to accept or reject based on the ratio. That's exactly the same as before. What we now need to make a decision is how are we going to update the interpolation set and I guess the trust region radius. So what we do is as follows. If things are going well, if we took a successful step, then we can maintain or increase lambda exactly as we did before. And it really doesn't matter what we do to the interpolation set. As long as you've got an invertible linear system afterwards, anything you like is allowable. In practice, there's better choices and worse choices, but you can do whatever you like for successful steps. If you have an unsuccessful step, if you're rejecting x plus s and you're going to stay at xk, what should you do? The first thing you should do is get rid of any faraway points. So if you've got any points that are too far away from your current iterate, replace that point with a new point that's inside your trust region, and don't change your radius. Don't shrink your radius. Just replace a faraway point with a point that's closer to xk. Okay, so now we've got an unsuccessful step and all our points are close to xk. Well, the next thing we need to look at is lambda poisedness. So what we're going to do is we're going to run one of these geometry replacement steps. So we're going to have a check of our lambda poisedness. If any of our Lagrange polynomials get too big, we're going to make one of these swaps. We're going to get rid of yi, we're going to replace it with this new value of y, and again, we're going to keep the trust region radius constant. If all of these fail, so we had an unsuccessful step, all of our points are close, and all of our Lagrange polynomials aren't too big, well, then we're guaranteed that we had a fully linear model. If both of these checks fail, we definitely had a good model, and we still had a bad step, which must mean that the trust region radius is too big. So in that case, we've got an unsuccessful step. We need to shrink our radius. And again, when we change our trust region radius, we're pretty much free to update our interpolation set however we like. So this is what the algorithm looks like. And the important part of all of this is on successful steps, it doesn't matter what we do because we're very happy with what's happening. If things are going badly, we first try and improve the model and we only shrink delta. Remember, delta has this really important role in model-based methods. We only shrink delta if we had a bad step and we know the model we used was good. If the model was bad, we always try and fix that first before updating delta k. That's how this algorithm works. And now we retain all the information we want. As long as update set in any manner is done in a sensible way, this is going to mean we do at most 2 evaluations of the objective per iteration. Once for f of x plus s, and once for whatever new point we might add to our interpolation set, rather than throwing out all the information. This does work in theory. The basic underlying idea of the theory is to show, based on that result I showed you about the generic geometry improvement algorithm, is you can't run these geometry improvement steps, these dealing with far points or bad points, infinitely often, in a row at least. You can only have finitely many consecutive iterations of that type. More specifically, let's just suppose that there's a universal upper bound on how many of these iterations we can possibly have, regardless of where we start. So let's just assume there's a universal upper bound. This is in fact true. There's quite a recent result to this effect that says if we run this on a p-dimensional polynomial space, such as linear or fully quadratic interpolation, then we can calculate G max is of order p log n. So p is the dimension of the polynomial space, number of interpolation points, n is the dimension of the problem. I'm not aware of a universal upper bound for minimum Frobenius norm interpolation, but we do know that there's only going to be finitely many at any point. We just don't have a universal bound regardless of the interpolation set. However, let's suppose that assumption does hold. Then the new version of our convergence result says that we do drive the true gradient below epsilon. That requires this many iterations or evaluations, because there's only 2 evaluations per iteration. We've still got the epsilon to the -2. We've still got all these constants, which are the same as the model-based method that we looked at yesterday. And now we've got a factor of G max out the front. Now, if we look at the evaluation bound, because that's the one that's very important, in the throw away all the points and rebuild things that we had last time, G max was just P. G max was the number of interpolation points. Now it's P log n. So we're slightly worse than this full resampling approach by a log factor. But in practice, this is the basis of good algorithms. This is how you make things work well in practice. So we're trying to kind of align what we do in practice with what we can prove results about. So that's the theory. The one thing I haven't really mentioned is what we do on successful or unsuccessful iterations when we are changing the radius. So I've said pretty much anything goes as long as you end up with something that's invertible after you do the update. In practice, you want to be careful. In practice, the best approach is to always add your trust region step. Always add in the new information that you got from your iteration, even if that information was bad. Even if you found that this point was bad, if you had an unsuccessful iteration, you should still add it to your interpolation set. And the reason for this is that I think I might have mentioned on Monday, if you add in a point that was bad, that tells the next model this is not a good place to look for the next step. So that is still useful information for the algorithm. Exactly how you choose which point to replace is kind of up to you, but typically you want to use the same ideas. We don't want to keep points that are very far away from our current iterate. We also want to think about points that are going to improve our lambda poisonous by a reasonable amount. So either replacing a point that's far away from xk, or a point that would improve the poisonous, which effectively means it has a large Lagrange polynomial in magnitude. So this is, for example, one approach that is used in some widely used software, where we multiply the absolute value of the Lagrange polynomial with a quantity that represents the distance to xk as a multiple of delta k. The power 3 here is basically saying we care a little bit more about points that are far away than we care about geometry, and this seems to work quite well in practice. My experience is actually even higher powers than 3 are also quite good. And I say, we're adding on successful steps. We add even on unsuccessful steps so that we know where not to look. Okay, that's the basis of the practical methods. Now, for the last little bit, I want to jump through some of these extensions to see what sort of issues we have to think about as we try and make this kind of basic idea more useful in practice. So the first thing I want to look at is simple constraints. So for example, what if I have bound constraints on my problem? More generally, the sort of framework that we can prove stuff about is where we've got a convex feasible set in Rn. So bounds, linear inequalities, these sorts of things. Fairly standard sort of results. There is standard derivative-based trust region theory for this setting. And there's not a lot of change you have to make to handle these constraints. The main thing you have to do is define a suitable measure of stationarity. We can't use the norm of the gradient as a sensible measure of convergence because we're not guaranteed that the gradient will go to 0 as we go to a KKT point. So instead, what we have to work with, there's a few different approaches, but one approach is to calculate this quantity here, where we minimize kind of a linear Taylor series while remaining feasible. This pi of x quantity that does reduce down to the norm of the gradient in the unconstrained case. So we've got a slightly different measure of stationarity, which we have to use inside our algorithm. We also have to think about what the Cauchy decrease step looks like in theory. So what does it mean to solve the trust region subproblem to sufficient accuracy if you're forced to remain inside a feasible region? So you've got to think a little bit more carefully about that. But once you come up with those ideas, all the theory works in a fairly reasonable way. But where the interesting issue comes in from the DFO perspective is model accuracy. So particularly with things like bounds, it can be very helpful. Sometimes it's essential for algorithms to be strictly feasible. So every time you evaluate the objective function, it has to be at a point that satisfies the constraints. If we've got bounds, we always know explicitly what they are. There's no DFO aspect to these constraints. So we can check it before we evaluate f at every point. You can imagine, for example, if your objective function has something like a square root or a log or something like that, then you definitely need bounds on your variables to ensure that you don't have nans or failed calculations coming through, for example. So strictly feasible methods can be very helpful. The problem is, if we build interpolation models using only feasible evaluations, we can't guarantee that the models are going to be fully linear without having those constants becoming potentially arbitrarily large, depending on the geometry of the feasible set. That you can't actually guarantee accurate models if you only use feasible evaluations. So this is where we need to do a little bit of work. What happens basically is that your fully linear definition is too strict. What we ask for are these two error bounds. So the objective value between our function and our model error is order delta squared. The gradient error is order delta. And this this error bound in the function values holds for all points inside the trust region. Now, this is too strict. This is what we can't achieve. However, if we're asking for a strictly feasible model, we don't actually care what happens to all the points inside the trust region. We only care what happens to the feasible points inside the trust region. So what we can do is we can change our definition to something that's easier to satisfy. This is something that I did a few years ago, where we modify our definition of fully linear to say instead of it being for all y, it's for all feasible y. And instead of the norm of our gradients being close, we care about how our gradient difference works when we inner product it with essentially a feasible search direction. So we've got a slightly weaker definition of fully linear. Again, in the unconstrained case, it reduces back. But we can use a weaker definition there. And now the question is, well, can this weaker notion be satisfied with feasible points? And I wouldn't be telling you this if the answer was no. The answer is yes. And all we have to do is change our definition of lambda poisedness. So if we're going to use lambda poisedness, but we're restricting ourselves to a feasible region, all we have to do is when we take the maximum over all y, we also constrain those y's to be feasible. And that gives us the upper bound on lambda that we care about. And this is the quantity that isn't going to grow too large, even if our feasible set has strange geometry. So this is still a reasonable value of lambda for things like linear interpolation. And what we can prove is exactly kind of the constrained version of this result. In one paper, I proved it for linear. In another paper, I proved it for MFN quadratic interpolation. But the same basic result. If all your points are close to xk and your set is lambda poised inside the feasible region, then the model is fully linear in this modified sense that adapts to the geometry of your feasible region. And so if you can do this, then you can get convergence of your algorithm. So you get this epsilon to the -2 complexity to drive your first order measure of stationarity below epsilon. So the modified algorithm then follows in kind of the usual way. All we have to do is come up with a more practical measure of measuring geometry in the feasible region. And again, there's geometry improvement algorithms that work exactly the same in the constrained case as the unconstrained case. Okay, that's for simple constraints. What if we've got general nonlinear constraints? So things like equality and inequality constraints. This is more complicated, and there's kind of a variety of approaches depending on where the derivative-free thing comes in. So is it the objective that's derivative-free? Is it the constraints that are derivative-free? Is it both? Is it some of the constraints but not all of them? Now there's more different scenarios that we have to think about. But basically, the main takeaway from my perspective on all of this is that there's a lot of different approaches for this sort of setting. There's some old works that look at the case where we only have derivative-free issues in the objective, but all the constraints we have full information for, and then we can handle them very explicitly. Other things look at, particularly for inequality constraints, looking at kind of reduced feasible sets inside your trust region that handle uncertainty in your models. There's derivative-free variants of standard nonlinear methods like augmented Lagrangian, sequential quadratic programming. There's other methods for inequality constraints that first try and reach feasibility, and only once they reach feasibility do they then worry about the objective value. So there's a whole bunch of different approaches that have been proposed. But in general, I would say this is an area that there hasn't really been kind of a settled kind of state of the art. So there's no kind of one solver that we can pull out and say, yeah, this is definitely the one you want to use as a default option if you don't know anything else. So if you have derivatives and you're doing large scale stuff, things like IP-opt are very standard. They're well used, they're well tested over many, many years, and people are pretty happy with how it works. There's a good kind of default choice. It's not always the best choice, but it's pretty good in pretty much most situations. I wouldn't say we're at that point for the DFO case when we handle constraints. I do want to mention probably the best attempt I've seen to hit that spot is a solver called Cobiqua. This was developed by a PhD student of Zaikun Zhang, who's giving the lecture tomorrow. A couple of years ago, it's been in the SciPy library, so standard Python scientific computing library, for a couple of years now. The way Cobiqua works is that it's an SQP method, sequential quadratic programming method. Basically speaking, and for those of you that know SQP, there's not really going to be any surprises here. What we do is we use the DFO type ideas to build interpolation models for both the objective and the constraints. Essentially, for SQP methods, you build a quadratic model for the objective and or for the Lagrangian, and linear models for the constraints. The constraints are also assumed to be derivative-free. Then we solve a more complicated trust region subproblem. It's essentially got linear constraints from these linearized constraint models. Then we have to decide whether a step is good or not. And the way we do that is by using a merit function. So a merit function is some kind of composite objective that measures all the goals we care about. In this case, our goals are decreasing F and ensuring feasibility. So what we do is we define phi of x to be our constraint violation. So in CopyCore happens to use L2 constraint violation. F of x there is our objective, and we take some large gamma and we take a linear combination of those and say, if we decrease this quantity, then we're happy. And so we use that to evaluate whether or not x plus s is a good point, accept or reject the step, update the interpolation step using these lambda poisedness ideas that I mentioned. That's how CopyQual works. But as I say, this seems to work reasonably well in SciPy, but I wouldn't say it's reached a point that it's considered kind of a standard default choice. What else? Noise. As I said, noisy problems is another really important use case for DFO where derivatives aren't going to be available. So I mentioned that again on Monday. So what we have to think about is what's going to happen to these algorithms when we have noise. So there's two types of noise I'll mention in the next few minutes. The first one is where the noise is uniformly bounded. So instead of there having access to the true objective, we only have access to some noisy objective value, f tilde. So in this situation, there's some upper bound on our noise. That could be because we have deterministic errors, or it could be because we have stochastic errors. The other thing I'll look at is proper stochastic noise, where our noisy objective values are unbiased in the sense that the true expected value matches the true objective function with some information about the distribution of this noise. The main difference between these two is that this stochastic noise, basically because of the central limit theorem, we can decrease the errors in our measured objective values by doing repeated sampling of our noise. So if we evaluate f tilde of x a bunch of times at the same value of x and take, for example, an average, then we can reduce the error in our approximations. In this deterministic/bounded noise case, I'm going to assume that you can't reduce the noise. So there's no way of doing averaging or anything like that to decrease the noise. You just always have to wear some error of size epsilon f. Why is this a problem? What happens to our algorithm if we just plug in noisy values for our objective whenever we use it? What it's going to mean is that our interpolation model gets less accurate because our interpolation model aims to fit to the values of f of x we have. If those values of f of x are wrong, then we're going to have a model that's less accurate to our function. The other issue, and it turns out this is the more severe issue, is that when we say, should we accept or reject a step, the way we do that is, have we decreased the objective value by a sufficiently large amount? And if we can't measure those objective values accurately, then we may make the wrong decision. We may accept a step that actually increases the objective because our noisy estimates did go down. So that one actually is the more complicated issue to deal with. But both these issues do arise. So first, let's look at this deterministic/bounded noise case. Let's take a simple case where we do finite differencing. So I'm going to do standard forward finite differencing just like I did over the last couple of days. But now I'm going to use noisy objective values every time I do that. What I can do very easily is measure my estimated gradient error. And previously, my error was proportional. It was a size order h, where h is the perturbation size. Once I add in noise, it's proportional to h, but there's another term that's proportional to the noise level divided by h. So now I can't improve my accuracy by taking h to 0 as soon as I have noise coming in. And this is something that many of us already know when you have finite differencing with round-off errors. If we optimize this error bound, if we minimize the error bound, turns out in an ideal world, you would take h to be of order square root noise level divided by the Lipschitz constant, and you would get a gradient error bound that's proportional to the square root of the Lipschitz constant times the error bound. In particular, square root epsilon f is the quantity appearing in both of these. So that's what you get in the optimal error bound. Unfortunately, in this situation, you're never going to know L in a practical DFO setting. So you can't actually compute the value of h unless you're careful about it. There's a paper here that finds a good way of estimating this value of h for finite differencing purposes. However, if we follow the same logic, let's say we're going to do interpolation. So we're going to interpolate to noisy function values. The fully linear type of error bounds we get look very much like this finite differencing estimate. So instead of the errors in our model being of size delta squared, They're of size delta squared plus something proportional to the noise level, which kind of makes sense. So MK here is constructed from noisy function values. And the error in the gradient looks a lot like the finite difference in case. It's proportional to size delta, but there's a term that's of size epsilon divided by delta. So we can't decrease, well, in fact, neither of these error bounds can be decreased all the way to zero. The gradient error bound is worse in the sense that as you keep decreasing delta, your error bound starts to grow again. So this is what happens in this situation. However, it might not be obvious, but it turns out if you just run a model-based DFO method with noisy function values without any modification to the algorithm, you just throw in the noisy values, it will still work. It will still decrease F reasonably well. If you do happen to know epsilon F, you can do additional safeguarding. But if you do no modification whatsoever, it will still work. But you won't be able to converge to a full solution, which makes perfect sense because if you've got noise that you can't get rid of, once you reach a region where all the function values are within that noise level, you have absolutely no way of knowing which point is better than any others. So we certainly can't converge to a full solution, but we can converge close to a solution. And it turns out, this is a recent result that I proved, that you do get a complexity bound that exactly matches the noise-free case. The only caveat is that you can't drive your gradient error all the way to zero. You can only decrease it down as small as a constant value that's proportional to the square root of the noise level that you're working with. So you can still run it, you can still decrease your function values, but you're never going to get all the way to a solution. You're going to get close to a solution where close depends on how large the noise is. One additional nice thing out of this analysis that I've hidden in all of here, but if you look into the constants, it turns out there's a nice practical heuristic that you can use that improves performance for noisy problems. And all you have to do is say, again, run everything without modification, but when we have unsuccessful iterations and we choose to shrink delta K, I've said so far that on unsuccessful iterations, we basically halve the size of delta K. That's pretty good when you don't have noise. When you do have noise, it does help to decrease delta more conservatively. So for example, decreasing by a factor of 0.98 rather than 0.5. This doesn't affect the convergence theory. As long as that constant is strictly less than 1, it still converges. But in practice for noise, it does help to have that constant closer to 1. And this theory that I've hidden inside the constants here does justify that as well. Okay, that's the case of bounded noise. Don't do anything, you can converge to a neighborhood. What about the case of stochastic noise? So for stochastic noise, as I say, we can always get better objective estimates if we take more samples and do something like averaging with high probability. As I say, when there's stochastic noise, there's always a chance of things going wrong. But in general, we can take more samples, we can get better estimates. So the first question we need to ask is, if we want to run our algorithm with noisy estimates of function values, how accurate do they need to be? And it turns out that if you take your entire model-based method and every time you need f of x, you compute a noisy value, and the error in that is of size delta squared, then everything works as before. You still get fully linear models, you get a sufficiently accurate, sufficient decrease check, and it all works perfectly well. So this is the condition we need to satisfy. And as I say, if we sample enough, you can achieve that. For example, there's standard theorems from probability theory. They're called concentration bounds. They look, for example, something like this. If our noisy function values are unbiased, so the mean is exactly the function value we're trying to measure, and the variance is bounded, is finite, and then we sample noisy values capital N times, then we can achieve the error that we want, order delta squared, with high probability, and the requirement is that N is sufficiently large. In particular, N grows like the variance. It grows as the failure probability gets smaller, and as delta gets smaller, N has to increase as well. That delta to the -4 comes basically from the central limit theorem type idea. So you can do it if you sample N sufficiently much, although we have to wear a small chance of failure. So in theory, this means that if at every point you take delta to the -4 samples of your noisy function, you should get sufficiently accurate estimates every time. Now, unfortunately, in an algorithm, delta goes to 0, so delta to the -4 grows very, very rapidly. It's completely impractical. for a practical algorithm. So in theory, you take this. In practice, something like delta to the -1 is a more reasonable alternative that still carries this idea of more samples as you start to converge. So the one thing I need to mention to finish all of this is to say that in theory, this sampling gives fully linear models and accurate decrease conditions, but only with high probability. There's still a chance of failure. So what happens to a trust region method if the information you give it is accurate, but not all of the time? It's accurate with high probability. Does the method still converge? And it turns out the answer is yes. So very roughly speaking, we're going to, if you impose some assumptions that say the model is fully linear with some sufficiently large probability, alpha m for model, and the estimates used to measure your sufficient decrease are sufficiently accurate, again, with some probability, then you can prove a convergence result. So what this says is that if these two probabilities are sufficiently large, for example, the product of them has to be strictly bigger than a half. There's more than that, but that is one of the requirements. If you do that, then you can measure the expected number of iterations required to achieve your convergence to any level epsilon. You still get a bound that's order epsilon to the -2, but this does grow in proportion to how small these alpha values are. If the alphas get closer to 1, then you get a faster convergence rate. So this does still work if things are fully linear with some probability, and you can still achieve any accuracy epsilon that you want because you're going to do improved sampling as you converge. Now, I know I'm very close to the end, so I will skip what I mentioned here for structured problems. This is looking at problems where you have some derivative-free information and some sort of more structured problem information. For example, if your function can be written as a composition of some vector-valued function that you don't have derivatives for, and some scalar-valued function that you have complete information about. So what happens if you have some information about the structure of the objective? It turns out that there's more that you can do, and things can be a little bit more careful. And this works when H is both smooth and non-smooth. I don't have time to mention that. I just want to wrap up by talking a little bit about software and sort of looking further ahead in the last couple of minutes. So in terms of what software, if you want to use these methods, what software is available, what should you use? I'd say the most widely used, most successful collection of software is a bunch of routines developed by MoCaO, who was a professor at Cambridge for many years. He died about 10 years ago. Zaikun, again, who's talking tomorrow, did a huge amount of work translating and really kind of refining the code. And he's got a package called Prima that collects all of these routines that were developed over about 20 years on his GitHub. And these handle different kind of problems with constraints. So nonlinear, unconstrained, bound constrained, linear constraints with different types of interpolation. They're very, very sophisticated methods. They do, at their heart, use this lambda poisedness idea, incremental updating of geometry, but there's much more sophisticated management of the trust region, much more sophisticated consideration of the linear algebra aspects, and a lot more. There's a nice summary in this paper here of the kind of core ideas. These do not match the convergence theory. They are very successful, but we don't have theory for them, with the exception of this short paper on local convergence, which addresses a question from Monday. Other software is available. I mentioned the Copy-Qua code, which is a more recent extension of this PAL-style approach to nonlinear constraints. I have some code that takes this bound constrained version of the software, re-implements it in Python, and adds a bunch of heuristics to improve its performance for noisy problems. I mentioned the Nomad software on the first day. This is not a model-based code. This is a direct search code, a MADS code, but its performance is greatly accelerated with all these model-based ideas. This can kind of handle everything, though. This can handle very, very broad varieties of problems. At its heart, it's not model-based, though. It just uses it for acceleration purposes. And there's a code called Astro. Sara, who's talking on Friday, is the lead developer of Astro. This is specifically designed for stochastic problems, particularly simulation-based optimization problems. And there's other packages. For example, I've got a package that specifically adapts for least squares problems. And there's another package that can do similar things and non-smooth compositions as well. Okay. So this is the end of what I wanted to say. I wanted to cover basically some of the core basics of the ideas, what makes a good algorithm in practice, what do we know about the theory, and how can we extend this in more use cases. There's a whole bunch still going on in terms of research. In terms of what's going on right now, I've seen recent papers, recent work For example, looking at improving the complexity analysis for these incremental geometry, these lambda poisedness approaches, looking at how do we better handle nonlinear constraints? How do we kind of, more robustly manage all of this? Looking at more complicated problem types. How do we look more at non-smooth problems or mixed integer or multi-objective or all these sorts of things? There's work looking at incorporating partial derivative information. Some of the structure might mean you actually have access to some gradients, but not others, for example, some partial derivatives. A little bit more work trying to align theory and high-performing software, which there's a bit of a disconnect at the moment. There's people working on just selecting your model from a bunch of possible interpolation models using AI-type methods. There's people looking at parallel evaluations and how you work to update a model when you can get multiple evaluations in parallel. But then you have things like race conditions and things you have to work on. There's a whole bunch of different stuff happening at the moment, just to kind of let you know of what some of the things that are happening. And so that's all I had to say, just to flag what's going to be happening for the rest of the week. So tomorrow, and remember the talk is 3 hours earlier, so it's at 11 a.m. Melbourne and Sydney time. On Thursday at that time, Zaikun Zhang is going to be talking about some of his work on large-scale methods, so solving large dimensional problems with dimensionality reduction techniques. On Friday at the same time, 11 a.m. Eastern time, Sara will look at what she's been doing. So that's the author of Astro, on her work on stochastic problems, simulation-based optimization. So that's everything. I will leave it there. This is another reference, another advertisement for this summary paper I've wrote that explains all the stuff I've mentioned. And I will leave it there and say thank you very much for your attention over the last few days. And hopefully we'll see you all on Thursday and Friday as well. If there's any questions, I'm happy to stay on for a couple of minutes as well.
Can I ask a question?
Yeah, of course.
Okay, so Lyndon, thank you very much. It was really very interesting. So my question is, when you replace the points, I mean, you take the point with the largest absolute value, right? So is there actually some difference if you include something with positive or negative? I mean, the big absolute value, but the sign.
Not that I'm aware of. I've not looked into it, but I don't expect, my intuition is that shouldn't matter too much. So if I go back to the picture here, for example, where x3 had a bad Lagrange polynomial because it's changing rapidly in the vertical direction, that means it's going to take large positive values up here, large negative values down there. So in theory, realistically, you could replace x3 with the point at the top or up down the bottom. It won't really make a huge difference from a theoretical point of view. So I would expect if you looked at positive or negative, it's just going to tell you essentially sort of a mirror image of which one you should look at.
Okay.
A priori, I don't think there's any easy way of deciding which one's going to be better or worse. I think at that point, it's just going to be the luck of, does your function happen to be decreasing more up or down, which you don't know about. That's just kind of pure luck, essentially, at that point. You could use an idea where you use your current model to estimate or predict the value of the function at the top and the bottom. Now, your model's not good. That's why you're changing it, but it's something. Something's better than nothing. So you could use that idea, and that's the sort of thing they do in direct search. But yeah, I just use the absolute value, and that seems to work fine for me.
All right. Okay. Thanks.
Okay. Well, in that case, I might stop the recording and say thanks everyone for your attention.
Yeah. Thank you.